I'm super excited to do this. I've never done this before. So, like, please keep telling me if you can't see or hear things, or if there's other stuff you want to talk about, or if you want me to run something back or explain something differently. Yeah, but I just thought we would talk about um, DSP basics. So I guess maybe starting off, like, what is DSP? DSP is stands for digital signal processing, and that is a really like wide-ranging concept that could mean anything from like um, processing data that's coming off of a sensor, like a temperature sensor, from like doing analytics on your email. In this context, we're going to be talking about processing musical signals. So how to create and manipulate audio on the computer from scratch. So, not sure where people are coming from or your sort of background or familiarity with this. So, I thought I would start sort of as close to the beginning, at least as I see it. Um, so, I prepared a little visual. Whoops, not that. All right, I got my notes. Sweet. So, yeah, I and this sort of turned into a blog post. I'll put this up after the stream, but thought maybe it would be wise to start with just some conversation about what sound is. Um, so, sound, as I understand it, when you strike some sort of physical object in the world, it starts shaking and vibrating. And when it's shaking and vibrating, it then transfers its energy, it's that shaking, into the air, creating areas where there's compressed pressure and then areas where there's less pressure. And those waves travel outward in sort of spherical waves out from the source of the disturbance to where you might be listening to it. So in this little like JavaScript animation I made, this is the microphone and this is some source of sound. And the way the microphone works is it has some sort of filament in it that responds to that shaking and turns that shaking into a voltage. So this is like what the microphone might measure if you were to look at an oscilloscope of the microphone at that moment in time. And in order to get this signal into a computer, though, because this is like a continuous signal, it has like infinite resolution. It's just a voltage wiggling exactly the same way the air was wiggling. We have to sample it. So the way that works is there's a little thing in your audio interface or on your computer called an analog to digital converter. And what it's doing, it's like a lab technician that sits there and it writes down the measurement, that voltage. It writes it down once every certain period. And we call that period the sampling rate. And usually it's doing that really, really fast, like 48,000 times per second. It's writing down another measurement. And so, we start with this continuous wave, and then when we get it into the computer, we have a bunch of numbers that represent that voltage over time. And it's all stair-steppy. And this leads to interesting things that we have to think about when we're making stuff on the computer. But of course, we don't actually have to start with a real-world sound. That's kind of the cool thing about DSP or synthesis in general. I guess you can do this in the analog domain as well. But you can just make up patterns of signal out of thin air and send them to your speakers and listen to them. So this is my thought of what is a DSP algorithm. Okay, so a DSP algorithm is something that operates on this signal. And we talked about the signal is really just a list of numbers representing that voltage over time. So one of the simplest things we can do, and we do this all the time when we're doing digital signal processing, is we can change the gain of the signal. So here's a DSP algorithm for doing that. This is in C++. So we have a function here called amp. It takes in some floating point number. So this is a decimal number representing that voltage. Takes in some other decimal number representing the gain, and it multiplies the two together and returns the result. So we've already started doing DSP as soon as we started multiplying numbers together. And of course, when we're doing that, we might want to be processing lots of samples at a time. So sometimes you'll see this in a different form where we actually take a list of samples in. This is a pointer to a list of floating point numbers representing some signal over time. This is some buffer that we're going to write those samples to. And then this is how many samples that we're going to write and the gain. And we just loop through writing the result of that multiplication into this buffer, this output buffer. So I'm curious, is that making sense to everyone watching? Does that work? Let me know if it doesn't. I'll loop back. Okay, so I promised you that we would do this from scratch. And here's the best nothing up my sleeves sort of version of that I can think of. We are going to write some DSP code using no external libraries or tools, just what we just talked about. We're going to do it in C++, and we're going to make something that we can actually listen to. We're going to make an oscillator. So I'm going to open up my code editor. We're going to go here. And we are going to, wait a second, we're going to make a directory. That's where I'm keeping my notes. All right, so we're going to add a directory. We'll call this stream001. Let's move into that directory. Okay. All right, and we're going to add a file. Let's call it main.c++. So if you've not programmed in C++ before, that's totally cool. We're actually going to start just by making like the program that you get when if you were to Google like hello world C++. What is the first program that we write in C++? So I might remember this wrong. I'm pretty sure the first thing that you do in here is that you have this thing. It's typically called argc. It's like the number of arguments that our program takes in when you run it from the command line. And then the second one, I'm getting a spam call. That's annoying. Shh, stop vibrating. Okay. Sorry about that. The second one is called argsv, and it's this list of the actual arguments. We're not actually going to be using either of these. But our program returns a number, and that tells the terminal that we're running it in whether or not the program completed successfully. So if everything goes well, we're going to return 0. So this is like the simplest C++ program. And to make it a little bit more interesting, because right now if we were to run this, it would just quit. It would quit happily. Oh, enlarge the text. Yes. Yes. How do I do that? Oh, this is funny. Let me Google how to change the font size in Vim. Okay, increase font size NeoVim. How do I do that? Oh, is there like a quick way to do it? Maybe set GUI font. That looks pretty good. Zoom in, just zoom in with your terminal. Okay, wait, I thought I tried that. Oh, all right, well, there you go. That's perfect. That's what I want. Okay. Let me get back to my notes over here. Oh no, my Twitch chat window. Where'd that go? Okay, hold on. So sorry about this.
I'm sticking to my story, okay?
Why does it automatically play things? That's so annoying. All right. All right, we're almost back. This is all going fine. Okay, no, but I want to go to. Okay, no, but I want to go to. Okay, no, but I want to go to. Okay, no, but I... Yeah, there we go. Okay, sweet. All right, so here's where we left off. Yeah, we actually want to write something to the terminal so that we can see that this program did something. So there's this stream that the standard library in C++ lets us write to. This is so that we can actually print to the terminal. So we're just gonna say hello. So we're gonna say hello world, and then we're gonna make a new line. Okay, and my compiler is complaining because it doesn't know what this is. So I'm going to include the header that contains this cout thing. It's in IO stream. Brilliant. Here's my terminal. So we're just going to say clang++ mains. So this is clang++ is the compiler. It's the C++ compiler. We're going to give it the source code that we want it to compile. And we're going to call this program oscillator. Oscillator. All right, I might not have spelled that right, but that's fine. Wait. Oh. -O, oscillator. Okay. Oh, does it need... It probably needs to know... what version of the standard library we're using. And this is why I have notes. Yeah, wait, why is it upset about that? I don't understand. Do I need to say more things? Hilarious. Wait a second. I was doing this earlier today. Can we use this trick? Yeah. Yeah, wait, that should have worked. Okay. Okay, this is fine. Let me just actually wait a second. Let me use a different compiler just to double check and make sure that I'm not doing something really silly. Oh my God, that's hilarious. I actually need to save the file. It was looking at a previous version of the file before I included the header. Everything is fine. It's all fine. Oops, okay. Sorry, I'm looking for the Twitch chat window. I had like a system and I messed it up. There we go. All right, everyone's still following along. I know we've had some bumps. We've had some early bumps, but I think things are going to go okay. All right. So we've created this program. Amazing. Good for us. If we run it, it says hello world. Great. That's everything we wanted out of this. Okay, but let's actually start doing some DSP. So I said earlier that DSP is just manipulating lists of numbers in real time. And the way your computer deals with that, there's like a kernel level piece of software. There's a really low level piece of software that sits there and it goes around and it asks other programs for the numbers that it's going to send to the sound card. And so what we're going to do is we're going to make a program that writes a bunch of numbers to the standard output, and then we're going to redirect those numbers to the sound card using a piece of software called aplay. So aplay comes with most Linux distributions, and it's just a way of redirecting, or you could play audio files with it. It's just a way of writing directly to your sound card. So this was the most like bare bones way I could think to do this. So we need to give it a list of numbers to write. Okay. So let's make a simple oscillator. So we're going to define a data structure. Say that by saying struct. Let's call it phasor. And I hope that will become clear why we're calling it that in a minute. So this is going to have a piece of data called phase. And this represents where we are in the waveform in time. And then we're going to have another piece of data called phi. That stands for the phase increment. And we're going to set it equal to, was it 0916666? Okay, magic number. And I will reveal why it is we're using that magic number. And we'll replace it with something better later. We're going to give this a method called next. And what this is going to do is it's going to give us the next sample in the signal. So what we want to do is we want to make a signal that starts at 0 and it ramps up to 1, and then it drops back down to 0 again, and then it ramps up to 1 and drops back down to 0. So we're going to make this kind of sawtooth shaped, this little ramp oscillator going from 0 to 1 over and over and over again. And so the way we're going to do that is we're going to increment this property called phase. So we're going to say phase plus equals the phase increment. So every time we call next, we're going to add the phase increment to the phase and increase it a little bit. Okay, but if we leave it here, okay, and then we're going to return the phase. Great. So we've got something that will generate the next sample, but there's a problem. If we leave it here, it's just going to keep ramping up and up and up and up and up forever. And we don't want that. So what we're going to do is we're going to say if the phase is greater than 1, so if we've reached the top of the ramp, then phase is equal to phase minus 1. So then we're just going to subtract 1 from it. And the reason we're doing this and not just setting it equal to 0 is we might have overshot 1 by a little bit, and that extra bit is important, and we want to save it. So we don't want to just go back down to 0. We want to save that little extra bit and start from whatever position in the ramp that we should be at. Okay, so we have our little phasor. Amazing. And then I said we're going to write to the standard out. The way we were writing to the standard out is meant for text. And we want to send raw data out. So we're going to do something kind of irresponsible, and we're going to write using this like low level C command. And most of the, if this part doesn't make sense, it doesn't matter. This is something that you're probably not ever going to need to do. But this bit is the important bit. This is the DSP. So what we're going to do is we're going to write a program that spits out about a second of audio. So we're going to say num samples. So this is the number of samples that we want to generate. And if we want a second, and the sample rate that my audio system is set to is 48,000 samples per second. So we need to generate 48,000 samples to get a second of audio. Okay, so then we can write a little for loop, and we can say for an I equals 0, if I is less than num samples, then increase I. All right. And then we need some place to store this data before we send it out to the output. So we're going to make a little array. It's a C-style array. We'll call it buffer. And it is equal in size to the number of samples. And the compiler will complain if I don't make this a const. So I'm going to make that a const, which just means I'm not going to change it. I'm just promising the compiler I'm not going to change that number. Okay. So then we're going to write into the buffer. So buffer sub I, the I position in the buffer, is equal to, wait, yeah, we didn't make an oscillator yet. Okay. So we're going to make an oscillator. We'll call it osc. And this is our phasor. So we've just instantiated one of these structs. And we can say osc.next. And I happen to know from experience that that's going to be way too loud. So we're going to multiply this by some smaller number just to make it a little quieter. Which is, that's our first DSP algorithm we talked about. We're going to make it quieter. Okay. So then we want to write out to the buffer. And like I said, you don't really need to follow this bit. It's not important. But all we're doing is writing raw data to the standard out of the program. And in order to do that, we need to tell where to write to, what buffer we want to write, where the data is, and how much data there is to write. So we're going to tell it that we're writing floats, and we are going to write that many of them. Okay, neat. And, is it standard out? Yeah, there we go. Okay. No, you don't know where, oh wait, I remember needing to do this. It couldn't automatically find the right header. So, okay, this is fine. We're gonna go ahead and just Google C right. Okay. Where do we find this header? We find it here. Amazing. Okay. Let me put this back. Oops. Okay. So we're going to put that header in. We weren't using that other one, so I deleted it. All right. Here we go. All right. Now it's happy. So let's compile that program again. Yay, it compiled. Okay, and what happens if we just run this right now? What do we see? We get a bunch of gibberish on the command line because it's just writing raw numbers out the command line. Okay, so in order to hear this, we're going to pipe this. We're going to send the output to the input of a different program using this pipe operator. So we're going to send it to A play. And we're going to tell it this is one channel of audio, right? There's not stereo going on. We just have a single channel of signal. And this is going to be a floating point number. Am I remembering how this works? Right? Is this real? The sample rate is 48,000 seconds. Messed up the sample rate, and that's why it sounded so low. We got 8,000 samples per second, but we should have just heard something. Was everyone able to hear that? Yay, we made sound. Okay, we made sound with nothing. We just have like some math and a compiler, and we're already making sound. I mean, I said earlier that you would never want to do this, but I mean, you might. Like, there's a bunch of really interesting musical practices that have to do with just manipulating raw data. Like, if you're really into byte beat, this might be a really cool way for you to make music. You know, there's like classical works that sort of work like this. Like Tristan Parrish is a composer I can think of that writes, you know, music out of like raw bits. So yeah, you could use this in your musical practice. Okay, but I got distracted. I wanted to change the sample rate on A play, and I don't remember how to do that. So too big. We're going to say A play -H. Okay. How do you change the sample rate? Oh, it's -R. Okay. That's fine. Let's hear this again, but at the right sample rate. Eeh, so buzzy. Um, okay. And it sounds kind of ugly. And the reason for that is because it's really sharp. There's no rounded corners on this shape. And that ends up making a lot of high frequency content. And actually, it makes so much high frequency content that we can't actually represent it with the sample rate that we have. So we get these things called artifacts, where the frequencies that are too high for our sample rate to capture end up folding over that frequency line and showing up as lower frequencies in the signal. And I think at another live stream we can talk about why that is and how to fix it. But for right now, I think we should just pat ourselves on the back for making some sound. But what if we wanted to make a different kind of timbre, one that wasn't so like mosquito-like? One really easy thing that we could do is we could turn this into a sine wave. So in order to do that, we can take our phasor and use it to compute the value of a sine wave. So all we need to do is wrap the output of next with this sine function and multiply it by 2 pi. Okay, we're going to import some of the standard C math stuff. Great. So now we're taking this phasor, multiplying it by 2 pi, and sending it into the sine function. And that means every period, every full ramp of the phasor is going to be instead one period of a sinusoid happening at whatever frequency the phasor is generated at. So let's see if that's true. Compile it again. Okay, and then we're going to play it. Yay! It's an A. Cool. Are there any questions about what we did so far? Is this making sense? Okay, cool. So our oscillator only knows how to play one note. It's playing a concert A. And that's what this magic number is. The phase increment that we're adding determines the frequency of the oscillator. And actually, what this number is equal to, let me just make sure that I'm not lying to you, what I'm about to say. It's the frequency divided by the sample rate. So that's where I got that magic number from. It's the frequency divided by the sample rate. So if we wanted to make our oscillator so that we could tune it to different notes, we can add another method to this. We could call it set frequency. And it'll take in 2 arguments. One of them is going to be, one of them is going to be the frequency. And one of them is going to be the sample rate. Okay, and all this is going to do is it's going to set phi equal to the frequency divided by the sample rate. So let's test out to see if this works. We'll make our oscillator, and then we'll say set frequency. What frequency should we do? Maybe do a lower one. I don't know. Let's do 300 hertz. Then maybe that'll be different enough. We can hear it. We said our sample rate is 48,000 hertz. Okay. So let's hear this. Now hear this. Okay, it's a little bit lower. What if we wanted it a lot lower? Let's do the A an octave lower. Cool. Maybe if I just compile this fast enough, we can make a melody. Ooh, bassy. Okay. So, I mean, this, we've been at this for, I don't know, 30 minutes, and we already have a very usable object. This is exactly how I would write a phasor if I was going to make an oscillator in one of my plugins. Oh yeah, we can save out a little bit of our work here because right now we're doing this sort of inline. We're computing the sine down here, but we could make this a little bit nicer on ourselves, and we could make a struct that's just for making sine waves. All right, I'm just going to copy paste a little bit what we got here. I could reuse the phasor object. Like I could give this a phasor. I don't know. I can't think of a compelling reason why not to. All right, we'll do that. We'll do that. Okay, and then we'll want to set the frequency on this too. Okay. Float. No. Okay. Great. So now we have this little sine oscillator object, and we can use this in our program instead. I mean, now we can just use its output directly. Let's make it a little less spacey. That was really, really low. I don't know. Let's do 500 hertz. Yay. Okay. So that's sort of rapidly approaching the end of what I planned. There's a bunch of other stuff we could do with this. We could make this oscillator make a more interesting timbre because the sine tone is kind of boring. We could take this and we could put it into a VST plugin and play it in a DAW. We could change directions and start talking about filters. I'm kind of curious what anyone watching thinks. What do you want to do, Sir Doris? I'm kind of interested to play with this a little bit more and see what we can do to come up with a more interesting timbre. So like one thing we could do is we could make multiple oscillators and we could use something called ring modulation. So with ring modulation, you have oscillators that have different frequencies and you multiply their output together. I guess maybe this is amplitude modulation. Ring modulation is a special case of that, and this may or may not be that. I don't remember. Okay. Oh, we'll make it into a VST? Okay. Sweet. Yes. Let's do that. I'll just finish this thought really quickly. Did you hear how that timbre was a little bit more complicated? It wasn't just a pure tone anymore. You get these what are called side bands. You get additional frequencies that you weren't necessarily expecting in the output by multiplying two signals together. That one sounded up kind of like a dial-up modem. I guess that ages me. Okay. So if we want to turn this into a plugin, one of the easiest ways that we can do this is using JUCE. And JUCE is like a really big library for making the GUI, and it has a bunch of signal processing stuff in it. And I think probably the most important thing, it lets you compile to cross-platform, to Linux, to Windows, to Mac, and make VST plugins out of your own code. I don't really use a lot of the insides of JUCE. I prefer to do all of the DSP myself because JUCE sort of is, it's very object oriented and it's very opinionated that you write things in its particular style. And I find that that style makes it harder to make my code portable, right? Because I might want to run it in a plugin. I might want to run it on a little tiny microcontroller. I might want to write it as a super collider UGen or a max MSP object. So I like to keep all of the DSP like this, just really simple, like header only objects that I can manipulate that contain no external dependencies. And that's part of the reason why I wanted to explain this concept like this, so that you're not like hooked on JUCE. You're not stuck using JUCE. Because it's a library, it's an open source library, it's been around for a long time, but it might go away. And then you'd be stuck with like a box of broken code, and that would be sad. I don't want that. Okay. Oh, do I have Producer installed? The easiest way to get started with JUCE, if you want to make your own plugins this way, and there are other ways to make plugins too, and we could talk about that another day. Do I have Producer? No, I don't have Producer. Can I install Producer? No. Can I install JUCE? Does that give me a Producer? Like if you're on Mac or Windows, this is a piece of software that you can just install. JUCE's project management tools. That sounds like what I want. Let's try that. Okay, give me that. Give me the software. Truly one of my favorite things about Linux. Just I ask the package manager for software and it delivers me software. Producer. Okay, now we have Producer. Great. All right. So let's start a new one because it remembers what I was doing. Okay. We are going to, oh, that is so silly. The drop-down menu appears on the wrong monitor. What do I do with that? Oh no. I'm actually have to take it over to the monitor that you can't see in order to do this. All right, new project. Yay. All right, and then we can take it back. Okay, so it has this like nice little, wizardy thing that we can walk through in order to make the project. So we're gonna wanna make a plugin. It's gonna be a basic plugin. And then you sort of go through these steps. Our plugin, good to use the absolute basics. Cool. Yeah. Okay, so this is going to be our oscillator. And then this next step is just asking me like what of these different libraries that I want in it. And honestly, we're not going to use any of this. I'm just going to leave it at its default state. But we could uncheck all of these and it would be fine. And then this is like what different operating systems do you want to run this on? Do you want to make a Mac version? Do you want to make a Windows version? That's the Visual Studio one. And this software is going to generate what we need in order to compile to those platforms. So just for right now, we're going to just do Linux makefile because we're on Linux right now, and that'll keep things simple. But it's not too bad. If you wanted to check one of these, it'll just generate. Maybe I'll leave this one checked just so you can see what happens. Okay, create project. All right, We want to do this in our live stream folder. So in stream 1, okay. Did it do it? Do I have to save? Is that the issue? Does it not know where JUCE is? What's happening? Okay, it may have run into a silly problem because we downloaded it from apt. So I happen to have JUCE checked out from the GitHub repository, so we're just going to go there and run the producer from there. JUCE, okay. Let's get the latest. Give me the latest JUCE. Good. That seems sad. I don't think we have time for that. Okay. Extras. Producer. Builds. No. That went too far. Okay. Wait, was I hasty? Did we already have one? Yeah, we already had one. Okay, I was being hasty. There we go. Let's try this. I think it remembered everything that we were doing. Oh no, it remembered absolutely nothing about what we were doing. Okay, so we'll do that again real quick. Oscillator. Plugin. We'll do this, and we're going to do the Linux makefile. Great. Okay, everything on defaults. Yeah, that's where I want to make the project. Oh, and there we go. Okay, it actually did stuff this time. And so what it did is it just generated a bunch of code for us. A JUCE plugin tends to have these two classes. It has the plugin processor, which is responsible for actually doing the digital signal processing. And it has the plugin editor, which is responsible for the user interface. And it generates a bunch of boilerplate code for us. These two classes, which it names them after we called our thing oscillator plugin. And it has a bunch of methods. Those have sort of default implementations that it provides. We're not going to talk about most of these. The one that's really important, is process block. Okay, so this is where we're going to do all of our work. And this is the function that actually does the DSP in a plugin, is process block. And remember earlier how I said there's this like really low level piece of software on your operating system. And this is true on Windows, on Mac, on Linux. It's just going around and asking every program that outputs audio to give it as many samples as it asks for as quickly as possible. And just goes from program to program saying like, give me 48,000 samples. And then that program has a very small time window in order to actually deliver all of those samples. So this is a result. The structure of this method is a result of that. So the DAW, the kernel level audio process is asking the digital audio workstation, like say you're working in Ableton Live or something. It asks Live, okay, give me the audio. I need to send it to the sound card. And then the DAW goes through and asks all of its processes, okay, give me the audio. And that ends up resulting in process block being called. And so JUCE hands us this audio buffer class. And we're responsible for filling that up with data in time for it to send it to the sound card. And if we miss, we get like nasty clicks and pops because there's now suddenly going to be discontinuities in the output waveform. so we have to be really fast. But our job is to fill up this buffer. And so this stuff is just us asking JUCE, what are the dimensions of this buffer? Like in most cases, it's going to be stereo. So we're going to be dealing with not just a single list of numbers, but actually two different lists of numbers. And we need to fill up both of those lists with data. And then we go through and we just clear out the buffer because it might be full of random crap and we don't want that. So we zero everything out. And then we go through channel by channel and we actually write some data out. So this is where we could stick our oscillator code. But I'm not going to actually edit it in here because this is not my editor of choice. And that was probably a little bit small, if I remember from earlier. Okay, so now we have oscillator plugin. Okay, and we have a source directory. So remember I said earlier about wanting to like not trust JUCE too much, like not get hooked on JUCE. We're gonna write our code in a separate location. All of the important bits that like are our special code, we're gonna keep it separate. So let's add a file. We'll call this oscillator.h. So this is a header file, and this is the thing that if you're writing a C++ program, this is what allows you to import code and use it in multiple places. So we're gonna say pragma once. Every time you write a header file, you do something like this at the beginning, just to make sure that it doesn't get included in the compilation multiple times. And if that's not making sense right now, just sort of ignore it. This just means only import this one time. Great. And then let's take our work from earlier. And we'll paste it in here. Okay, we need to import some stuff. We'll see the math stuff. Okay, so we have CMath now. All right, and we have our two classes. That's cool. Okay, and now we can use them from the plugin processor. So in order to use them, we go through and we actually include the header that we just made. So we're going to include oscillator.h. And then we're going to give this class, this processor, a piece of data that represents our oscillator. So I guess we'll do that down here. We'll make it private. Why not? Okay, sine oscillator, oscillator. Sweet. Okay, so even right now, having done nothing, our oscillator's all geared up to play concert A. So what we need to do is go down to the process block function. Here we are. Okay, and then we need to actually write that data out. So in order to do that, we need to know how many samples to write. And the buffer knows how big it is. So a little bit like before, right? This should look a little bit familiar. We're going to fill up some buffer and then we're going to send it to an output. So we're going to say int I equals 0, I is less than buffer dot get number of samples. Was that it? Get num samples plus plus I. Great. And I'm going to actually make a little temporary buffer here. And we're going to fill this up with samples. And then we're going to write it to the other buffer. And the reason I'm doing it that way, I don't know, is that confusing? That's probably confusing. We don't actually have to do it that way. Well, let's write all of the left information, and then we'll write all of the right information. Okay, wait a second. JUCE already did this for us. We just need to move this loop inside the other one. So, okay, this outer loop, we're looping through the channels, right? So left channel followed by the right channel. And then inside, we're going to loop through all of the different places in the buffer, all the different time points that we want to write to. So we'll just make this little float called output. And this is going to be our, where we'll call next, and we'll advance the oscillator. We'll get the next output of the oscillator. And then we will write, okay, we have channel data. I think we can do this. And we can just say this is output. I might be wrong about this, and it's going to make horrible noises, and then we'll figure it out. Okay, so this is going to happen twice. Oh, wait a second. This is totally not going to work. Let's invert the order of this. I was about to try to explain why it's going to work, and then I saw that no, this is like really wrong. Okay, so we're gonna loop through all of the different time points, and then on the inside we're going to loop through the left channel and then the right channel. And so at each time point we calculate the next output value of the oscillator, and then we write that out to each channel. That's what the inner loop is doing. Okay, I think this might actually work. So then we need to actually compile this thing. And a pro juicer build has already made this handy little make file for us. And make files are just a way of, earlier how we were calling Clang from the command line, like this. This is like a way of saving those commands and reusing them. So it's going to handle like all of the including of the libraries and all of the like actual formatting of that compile command, so that we don't have to worry about it. So we'll go into that directory. We'll go into the build directory. We'll go into the Linux makefile directory, and then we'll say make. And now it's going to actually compile our plugin. And if it works, it'll actually install our plugin at a place where we can get it. Ooh, progress. Remember when I said that JUCE was really big? This is one of the downsides of working with a really big library. It takes a long time to compile. Oh, I made tea. This is why I made tea. Oh, I hope you're not getting like gross ASMR of me drinking tea. I'm gonna try to do that away from the microphone. Okay. Are there any questions about like what we just did? So we just did a lot of stuff. Ooh, linking. That's the last step of the compile process. Yes. Wait, what? Oh, it's making a standalone. That's weird. Okay, I think we were successful. This is exciting. Let's find out. I'm gonna launch Reaper. Good old Reaper. There's a new version of Reaper. But we don't care about that right now because we are so excited to hear our oscillator. Oh God, is it gonna be really loud? Wait a second. Let me turn down this track. I'm scared. Okay. Yay! It's a tone. Okay. We just made a VST plugin that is like a pitch pipe, I guess. I don't know. Maybe this is useful. Cool. Good for us. So, okay, and this is the default UI that JUCE gives you, not necessarily the most interesting. Okay, what should we do next? Should we make it so you can retune the oscillator? Do you want to make the oscillator make a different sound? We can make it respond to a MIDI note. I feel like it would be kind of cool to make it so we could change the pitch. Why don't we start there? Okay, I'll leave. No, I'll close Reaper. Good night, Reaper. No, we don't need to save that. Okay, so if we want to make this thing play a pitch, it would be nice for it to respond. Okay, nice. Yeah. It would be nice if it would respond to MIDI notes. So the producer gives you these little things that you can check, and this will cause it to compile differently so that it will appear as a VSTi, a VST instrument, instead of just a VST plugin. So we're going to say plugin is a synth. Plugin has MIDI input. And then, okay, we're going to turn off standalone because we don't actually want that. And it's kind of wasting our time. All right, yeah, let's only compile what we want to compile. Great. So it's an audio plugin. We're going to leave all this blank. It is a synth. Great. I don't care about the audio unit type. All right, so here's this is the important bit. It automatically set this as an instrument for us when we changed it to say plugin as a synth. So now it should show up as a VSTi. That is good news. Yeah, I don't think there's anything else that we need to do here. All right, so if we save this, it's going to go ahead and regenerate that makefile so that it compiles it as a VSTi. And the next thing that we need to do is then make use of this second argument that we ignored earlier for the MIDI messages. Okay, but there's something that I want to do first because it's actually really annoying me that there's red squiggly text. It's making my brain go crazy. So let's clean. We're going to use a piece of software called Bear to generate something that my editor understands so that my editor knows that there's not like a compilation problem. So we're just going to compile it again. And while that's cooking, we can talk about what to do with this MIDI buffer. So the MIDI buffer, where does it send? Oh, is it going to 3 every time I do that? That's probably why. Yeah, oh my, that's hilarious. All right, let's bring this back to our actual workstation. Awesome. So JUCE, MIDI buffer, what does this class do? So this is the second argument that we got handed. Wait, okay, I'm sorry. I'm randomly going silent because I wanted to find the window where I had the Twitch stuff. No. Oh, yeah, there it is. Okay, great. Good for me. Let's put that there. Okay. So this is the second argument that we got handed. So it can tell us a number of things. It can tell us like how many MIDI events are there in this period of time. And then it can tell us like what is the first time of the buffer. Oh, okay, and then it can find the next sample position. So here's my mental image of what this is. Much like the audio buffer, it's just a big list of data. Each one of those pieces of data is a MIDI message, so that will contain which note got pressed, whether it was a note on or a note off, what the velocity of that note was, how loud it was. And it has, all of those events have timestamps. So the kind of tricky thing that we have to do is we have to line up those timestamps with the right point in the audio buffer and set the frequency at that point in the audio buffer. So I think what we want is this find next sample position. I think this is the handy method here. There's like a bunch of other crap on this, but I think this is the one that we want. Because this lets us use this integer sample position to search for the next event. And this hands us back a MIDI buffer iterator. Okay, and the MIDI buffer iterator lets us actually get the MIDI message data. And is it this one? This is like the kind of thing that you sort of do once a plugin, and then my brain just like off deletes that information as soon as I'm done with it. Okay, you know what? Let's cheat. Let's look at one that I've already done. Oh, development, Fellhouse Audio, Fellhouse DSP. Let's look at the plugin that I just released. Fell analog. Wait, where are you? Oh, is it in here? I think it's in there. Fell analog head. Fell analog head. Okay. So we want the plugin processor. We're going to reference how we did this here. I'm going to skip past the stuff that we don't need. Aha, okay. So here's where we're actually processing the MIDI messages. And what did we choose to do? Oh, okay. So we pulled we pulled all of the like processing outside of this loop. We made up another buffer to write into. Yeah, that's right. And then I had a different method here of writing sample information in bulk. So what's the simple way to do this? All right. So I think what we can do, is while we're in here, we're looping through the number of samples, and we have this thing I. So I think we can say MIDI messages.get next sample position. Ooh, our compilation was done. I think we can make the editor stop screaming at us. Yes. 1, 2. Oops. Compile commands. Up 2 layers, please. Okay. All right. So I think we can get the next sample position. Let's see. What was that called? Find next sample position. And this returns us an iterator. Oh, we have to, okay, yeah. We have to tell it which sample we're interested in. So I think we can feed it in I. All right, so give me the next one after I. And this gives us our MIDI iterator. Oh, auto with a 0. All right, MIDI iterator. Good for us. And then what did we do with this? Because I think we used that method over here, did we? We're saying iterator got... Oh, no, we're just looping through all of the MIDI messages. Okay, but we could say iterator.getMessage. This will be like a little bit less than ideal. There's probably a more efficient way to do this, but we don't care right now. We're just going to do this the simplest way that we can. So we're going to say, oh my God, I'm like a goldfish. What was it? Get message. So this gives us our iterator. We're going to say get message. Okay, this gives us a message. And the message type, okay, we can find the message type. We got it from the MIDI buffer iterator, and then this has get message. Yeah, where's the documentation for that? Come on. MIDI message? What do you got for me? Okay, this is where I wanted to be. Right? Aha, yeah, and this gives me the timestamp. Okay, so I think then we can say, all right, this is our message. I think we can say if let's get timestamp, right? Is less than or equal to I. Then we want to set the frequency of our osc. So osc.set frequency. And then I think the message has like a little handy method on it to get the frequency. And if not, that's like no big deal. We can write that ourselves. What do you have for me? Oh God, there's so many constructors for this. Oh, that creates. We don't want to create messages. We just want to get the data. I feel like I skipped a step here. MIDI buffer iterator. What did we do in the other plugin? It said get message, get note number. Oh yeah, get MIDI note in hertz. That's handy. Okay, so this is our little two-step thing that we can do. Okay, so we get the note. And we set the frequency on the note. I think we only want to do this if it's a note on, though. So if message.is note on, is that a thing? Yeah, I think that's a thing. So if it's a note on, then we will set the frequency. And then, okay, we're going to have a little thing in here for the gain, too. So we'll say auto gain is equal to 0. And then if it's a note on, then gain is equal to 1. Yeah, it's equal to 1. All right, amazing. And then we'll just scale our output by that gain. Yay. Okay, so now it won't constantly be screaming at us. And we should be able to, it'll turn on when the MIDI note comes in. It'll set its pitch to the actual value of the frequency value associated with that MIDI note. And all should be happy. Except I probably made a compile error, and this is going to get really mad at me. Okay. Get message is not real. Really? But. It's real over here. What's different? Yeah, they just loop through them. I mean, it sure doesn't have a get message method here. Where is that? What class is that on? Because that's the one we want. Oh, it's on a metadata. How do we get a metadata? Oh, we need to dereference it? Oh, okay. Okay. So this is because of pointers. And I can go into that if you would like. Oh, and this needs the sample rate. And I think we know about the sample rate here, do we? Okay, let's hard code this for now. This is an irresponsible thing to do to hard code this, but that's fine. We just want to get this compiling. We can come back and make it better later. Okay, and I think if we run this, it might just crash, because I bet that this is going to be a null pointer when there's no messages. So we might need to put this. We might need to put this all in a big if check. Does the iterator give us anything handy? Does it tell us like I have more stuff, or I'm at the end? I know one thing we could do. We could say if. Let's find out if it crashes. I'm worrying maybe more than I should, but I think it's gonna crash. Oscillator. Oh, it's not a VSTi. This is our. That's weird. I think it's the new plugin though. it didn't change over to a VSTI. That might be an issue. Okay, we are not hearing sound. It's not really upset, and it's not very happy either. Okay. Fun. I wonder if we should just give up on these for loops and do this more like we were doing in the other one, because I think there's a reason why we were doing it the way we were doing it in the other plugin. I'm kind of tempted to do that. Okay, so that would mean that we have some sample position, and we're gonna do a while loop. So we're gonna say, oh no, we're gonna iterate through our MIDI. We're gonna iterate through our MIDI messages. So we're gonna say for auto iterator in MIDI messages. Is it 2? No, it's not 2. Why are you mad? What's the deal? Oh, it can't be a reference. Okay, that's fine. Okay, and then we don't need this. Okay, and then we don't need that. And this is just going to be this iterator. So now we don't need to worry about the next sample position or any of that stuff. We're actually looping through the MIDI messages. And each time we find one, we're going to set the frequency. And then we're going to find the message sample position, and we're going to figure out how many samples we need to process. So we're looping through. We've done nothing. We're looping through, and then we get a message, and we go, okay, we have this message. We have this message sample position. And then we set the frequency, and then we have this other for loop where we say int I is equal to 0, I is less than sample position message sample position minus sample position. This is kind of an unclear way of saying this. Maybe let's call this remaining samples. Oh. Okay, wait a second. We can do this way simpler with a while loop. So while sample position is less than message sample position, we are going to actually make our output, and then we are going to increment sample position. Okay. And then the place that we're writing to is in sample position. Okay, good for us. Now, the only issue with the way that we've written this is that at the very end, there may be some time where we don't have any MIDI messages, where we've processed our MIDI messages, but there's still more sound information to write. So now we can write a little catch-all loop down here where we say, while sample position is less than buffer dot get number of samples, then we'll do this thing again. Right. And there's a cleaner way that we could write this. Right, we're being kind of repetitive here, but that's okay. This is fine. We just want to see if this works. I'm signing back on briefly because I figured it out. And I want to put this in the highlights on YouTube later. It was so simple and so silly. The first time we compiled the plugin, it was as an audio effect. An audio effect has input channels, right? If it's default to stereo, it has 2 input channels. Look at this loop. Let me make it bigger. Maybe a little bigger than that. Okay. These loops that I just copy pasted from the basic JUCE setup are looping through the input channels. When we changed it over to an instrument, which typically has no audio inputs and only audio outputs, this turned to 0. And if this is 0, we don't iterate here. We don't actually write any channel data out. So that's why it was always silent. So in order to fix this, we can change this to output channels. Okay. So I changed a few other things while the stream wasn't on. So let me just walk through what I changed. I added a float here for the gain. I added something to represent the sample rate. Then in the audio processor, there's this method here called prepare to play. And this gets called when the DAW loads up the plugin and is getting ready to ask it to make sound. And it hands it some useful information for making sound, like the sample rate and the number of samples per block that it's going to ask for. So like each time process block gets called, this is going to be the buffer size, is the number of samples per block. Okay, so I added that. And then down here, this looks like where we left off. And I'll just walk through this from top to bottom. So we save off the total number of input channels and the total number of output channels. So we asked JUCE what those are. This one is now 0. This one is now 2. Okay, we go through and we clear out our buffer because the buffers initialize with random garbage in them, and that could we could end up sending that garbage out to the sound card, and that would not be good. It would sound bad. Okay, then we create this little temporary piece of state for keeping track of which sample it is that we are currently writing out. And then we start iterating through our MIDI messages. So as soon as we find a message, we ask for its sample position. And then we go and we process all of the samples up until that sample position. So that's going to get us up into the point where we press the MIDI note. Because the block might not perfectly line up with where we press the MIDI note. There's going to be a little bit of sound before and there might be a little bit of sound after. Okay, so we go through, we multiply the output of our oscillator by the gain. We go through our output channels one by one. And then we set the channel data to that output. We increment our sample position. So this will just keep going until we catch up to our MIDI message. And once we're at the point in time where the MIDI message drops, we check to see if it's a note on. And if it's a note on, then we actually set the frequency of the oscillator and we set the gain to 1. And if it's a note off, then we set the gain to 0. That way the oscillator is not constantly on and screaming at us. So it's only when we're holding down the key that we get some sound. And then, like I said, the last MIDI message is going to leave off, and there might still be a little bit of room left in the buffer. So this bottom loop is just to catch that case, right? So sample position is still less than the number of the number of samples in the buffer. So we have to keep processing. So we just go through, and whatever state the oscillator's in, we just say next, 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 next. And we write that out to the left and right channel. Okay. So that's that. We're going to compile it. Okay. Good deal. And then we are going to find our oscillator plugin. Good. It's not making sound. We don't want it to make sound right now. But when we get the MIDI going, it makes sound. It's kind of loud. Okay, it's a monophonic oscillator, monophonic synth. It makes sound. Its envelope is terrible. It sounds really bad when I let it go. And that's because we're like setting the gain instantaneously to 1 and then setting the gain instantaneously to 0. So we get this nasty like pop at the beginning of the sound and at the end of the sound. But I think that's pretty good. That's a good spot to leave things for today. Okay, I'll post this on YouTube later. Good night. Have a good night. Goodbye.